design for testability is like call of the arms. All chips that are designed have the facility to test it. So our aim is to think that whether that testable part can be exploited in some form or not. Now, scan chains are a very popular way to test a design. In a scan chain, basically, for example, if a design has some registers, a scan chain is actually an interconnection of all the registers in a serial fashion. That is, the registers are connected in succession, and a user or a tester can input any data, and at the same time, he can output any data from the scan chain in a serial fashion. This is the example of a typical scan chain. We have a series of flip-flops, and they are connected in succession, and we have a scan in line and a scan out line, and a test clock, which is asserted to operate the chip in a test mode. So the chip has two modes, normal mode and test mode. The user can alternate between the two modes. He he operates the chip in a normal mode, then he asserts the test mode, takes out the data, and compares it with some pre-prescribed format to test whether the design is functioning right or not. So this is the testable part. This is how scan chain based testing works. Yes, now let's see, can this be attacked or not? Scan based attacks. So see, what does actually scan testing give in the hand of an attacker? An attacker can at any point of time stop the execution of an algorithm and just scan out the intermediate state of the algorithm. So by doing that, you will be able to get all the intermediate state values of that algorithm. And from cryptographic point of view, that's very handy, because knowledge of the intermediate state of the cipher can very much reduce the complexity to break it. And we show it that it's really possible that by tapping that information, we can mount an attack. So one of the very popular examples is that we use these pay TV set-top boxes in our homes. So actually scan-based attacks have been successfully applied to these for a very few dollars to get the keys of that. So it's very nice, you could be watching free movies at your home and just by mounting the scan-based attacks. Okay, now let's get deeper into that. The attack can be roughly divided into two phases. The first phase is where we actually ascertain the structure of the scan chain. Okay, one thing which has to be clarified, that is, a scan chain, when I tell about a scan chain, so the scan chain can be any random structure. For example, if a design has 5 registers, the scan chain will have the 5 registers connected in succession. But what is the way they are connected, means which one after another, that's not known. Means it can be all the factorial 5 ways that the registers can be connected. So the first phase of the attack is to ascertain that, okay, which bit of the algorithm corresponds to which register. When I scan out, otherwise I will not be able to interpret the data, what I am scanning out, that which is what. I should be able to identify that. And the second part is deciphering the cryptogram, which we will explain, will be clear in the subsequent slides. So what our study reveals is that due to the design methodology of stream ciphers, they are specifically vulnerable to the first phase of the attack. But the second phase is conditional. It depends on the algorithm. Actually, it depends on the fact that whether we are able to track back to the previous state of the cipher from the knowledge of the present state. Okay, I think I should skip this because a lot of discussions have been going on stream ciphers. And also the stream project, everybody is familiar, I think. Okay, this is the final portfolio after the revision in September 2008. So there is a total of 7 ciphers that have been selected, and our focus is Trivium. And as you can see, Trivium is a hardware-based stream cipher, and our attack is a hardware-based attack. So it's very relevant in that point of view. Mounting a hardware-based attack on a stream cipher which is hardware-focused. So this is a brief overview of the Trivium stream cipher. It takes 80-bit input and key and 80-bit initial vector, and also it has got a 288-bit internal state register. As any other stream cipher, it contains the key initialization and the key stream generation phases, and it XORs too, means the key mixing is XOR. Now these are the specifications. As you can see, in the first 3 steps, basically the key and the IV are assigned to these states. These are the 288-bit states, and these are the fixed points in the algorithm. These fixed points also get assigned. Then this particular function is iterated for 4 cross, that's not dot, that's cross actually, cross 288 times to complete the key setup phase. And next is the key stream generation. As you can see, basically 15 specific state bits are used to non-linearly update 3 specific state bits, and everything else is a shift. So this is the specifications. Now, as it's a hardware-based attack, so it should be very clear with the implementation that we are attacking. The implementation that we have taken up for the attack is available on the InSteam website. It's by Tim Good and his colleagues, and this is the particular architecture. So, what as you can see, it contains basically shift registers. There are 288-bit shift registers. They have been broken, but anyways, they form the 28-bit parts. They have got T3, T1, T2. These are the temporary bit registers.